Welcome to an application of multivariable calculus, the moment of inertia for a solid cone. We will briefly review polar coordinates, cylindrical coordinates, and triple integrals, and then we will find the moment of inertia for this solid cone by using a triple integral in cylindrical coordinates. What will we do in this video? We will define the moment of inertia I for a solid by the formula rotational kinetic energy equals 1/2 I omega squared. We will define the cylindrical coordinate system r, theta, and z, which is a three-dimensional coordinate system. We will find that the differential volume in this coordinate system dv equals r dr dz d theta. We will then approximate the kinetic energy of a cone rotating at an angular velocity around a particular axis by a Riemann sum. This angular velocity is denoted omega. We'll look at a limit of these Riemann sums, and in this limit, the Riemann sum will approach a triple integral. We will evaluate this triple integral by using an iterated integral in cylindrical coordinates, and by evaluating that integral and using the relationship between the kinetic energy of that rotating cone and this equation up here for the moment of inertia, we will eventually show that the moment of inertia is equal to 3/10 r squared times m for a cone. This turns out to be a formula that can be used for any cone of uniform mass density. It doesn't depend specifically on the mass density. That is kind of hidden in the mass here and the radius of the cone right here. Interestingly, a cone has a particular radius and a particular height, and when we got this formula for the moment of inertia, it did not involve the height. Well, that's kind of hidden in the calculation because the mass of the cone does depend on the radius and the height of the cone, but this is how algebraically it works out to a very simple formula. I hope that you will enjoy the derivation of this moment of inertia during this video. First, let's discuss the moment of inertia, which we will represent by the letter capital I. Suppose we have a rigid body having a mass m that is rotating about some axis A. So here's the mass, here's the axis A, which in this case happens to be an axis of symmetry, but it doesn't need to be. And this mass is rotating about this axis. We will define the moment of inertia I about that given axis of rotation A. Let's suppose this mass is rotating about that axis A with angular speed omega, and the resulting rotational kinetic energy is k sub r. We'll use this little subscript here to remind us that we're looking at the kinetic energy of rotation. So when this mass spins around this axis, all of the little pieces of this mass are moving with certain velocities, and if you have a mass moving with a certain velocity, we can define an energy associated with that motion. We would add up basically all of the kinetic energies for all of the particles making up this mass that are rotating around this axis. We will then say that the moment of inertia I is defined by this equation, that kinetic energy of this mass is going to be 1/2 I times omega squared. So we used omega to represent the angular speed. So what is this angular speed? What do we mean by this angular speed? Well, suppose that we have a mass that is revolving around some axis in a, let's say, circular orbit. Let's suppose the mass m, this mass right here, makes one complete revolution through 2 pi radians in an amount capital T seconds. Well, in that case, we have a periodic motion with period t seconds, and we will define the angular speed of this mass as the angular speed equals 2 pi measured in radians divided by t, which in this example we measured in seconds. So in this example I have measured omega in terms of radians per second. We'll almost always talk about radians when we're talking about omega, but of course t could be measured in seconds, hours, years, whatever. So what are the units of measure for this angular momentum I? Well, we have the equation which we used as the defining equation for I. The kinetic energy of rotation was 1/2 I omega squared. Well, the kinetic energy, which is energy, has the same units as an energy, let's say, measured as m times the velocity squared. And so that would be mass, and then velocity is distance divided by time. And since we have a square here, we have a square here. So what we could say is if we have omega equal to 2 pi over t, where t is time, then omega has units 1 over time. I then has the units of the kinetic energy of rotation divided by 1/2 omega squared. The kinetic energy has units of mass times distance over time squared, and then omega has units of 1 over time squared. This is dimensional analysis, I guess you could say. We could be measuring mass in grams, we could be measuring distances in meters, we could be measuring time in seconds, for instance. But if you look at this, there's some cancellation going on. It can be simplified to mass times a distance squared. For instance, we could measure the angular momentum in units of kilograms, which is a mass, times meter squared, which is a distance squared. Let's talk about the rotational kinetic energy of a point mass revolving around an axis. Suppose we have a point mass m that revolves about an axis at a distance r with constant angular speed omega radians per second. So in time t seconds, the distance the mass m travels around this axis is going to be omega times r times that period of time t. The instantaneous speed of the mass around the axis then, actually I guess I should say the average speed, but we're also assuming that the speed doesn't change, so it is the instantaneous speed also. The instantaneous speed of the mass about the axis is the speed v equals the distance traveled by that mass divided by time, and the distance was r omega t, and time interval was t, and this simplifies to r times omega. So that's the instantaneous speed due to that rotation of the mass around this axis here. So the rotational kinetic energy of this mass about that axis is, the rotational kinetic energy k sub r is 1/2 mv squared, but the velocity, remember, was r omega. And so this simplifies to 1/2 m r squared omega squared. Here's a short example of these concepts. Suppose we have a mass of 2 kilograms that's revolving 3 meters from its axis of rotation at 5 times per second. Then we will have that omega is going to be 10 pi divided by seconds, 10 pi radians per second. Every second, this mass goes around the axis 5 times. 5 times 2 pi is 10 pi. So in that case, the kinetic energy given by 1/2 mr squared omega squared is going to be 1/2 the mass is 2 kilograms, the radius is 3 meters, and that's squared as we see here, and the value of omega, 10 pi per second, is also squared as we can see here. And if you multiply all these down and do the arithmetic, what you get is 900 pi square kilogram times meter squared per second squared. Now, if we think about it for a minute, kilogram times meter squared divided by second squared, this is a unit of energy which we called the joule. And so the kinetic energy of rotation is 900 pi square joules. Notice that we got a pi square here, and that was because we had an omega squared here, and omega happened to depend on pi. To find the kinetic energy of a cone rotating about its axis of symmetry with angular velocity omega, we will first partition the solid cone into subregions. For each subregion, we will find the volume of that subregion, find the mass of that subregion, find the distance r from the subregion to the axis of rotation. And if the cone is rotating with angular velocity omega, we will find its kinetic energy of that subregion, and then add up the kinetic energies of rotation for all of these small subregions to find the total kinetic energy of that rotating cone. When we follow this procedure, what we get will be a Riemann sum for a triple integral. When we let the number of small mass particles rotating about the axis, the number go to infinity, our Riemann sum can be written as a triple integral. So we will use a triple integral to calculate the total kinetic energy of rotation. So we will focus on a solid cone that is rotating about its axis of symmetry, and we will set up an integral for the kinetic energy in terms of cylindrical coordinates, a triple integral in cylindrical coordinates. We will then use that to compute I. I will depend just on the geometry of the object, in this case a cone, and its mass. By adding up the kinetic energy of rotation for all of the masses comprising the cone, we can compute via a triple integral the total kinetic energy due to rotation. And this integral that we will set up, we will evaluate by using cylindrical coordinates. So let's talk about cylindrical coordinates. Hopefully you have seen them in the past, so this will be a short review. Now let's introduce cylindrical coordinates. Let's suppose that in three-dimensional space we have an x-axis, a y-axis, and a z-axis. We want to associate with a point out here in three-dimensional space cylindrical coordinates r, theta, and z. To get these coordinates, we will start at this point and drop a perpendicular down to the xy plane. This point in the plane we can find polar coordinates for, r and theta. Then we can attach to that one more coordinate, z, and get cylindrical coordinates of this point, r, theta, and z. So the cylindrical coordinates of this point are r, theta, and z. And we can say that just like polar coordinates, cylindrical coordinates is just like polar coordinates, but with an additional z coordinate. Let's review, or let's look at that calculation we just saw from a different perspective. This is not quite as rigorous, so maybe a little bit of hand waving here, but a hand waving perspective on cylindrical volume elements. here is that volume element that we just saw. And if the dimensions of the volume element are small, if these delta whatevers are all small, this will be almost a rectangular box. This one doesn't look rectangular because delta R is quite large here. But if it's small, if those are small, the curved edges become almost straight and opposite sides have just about the same dimensions. It's similar to what you saw in Calculus 1. If you take a small piece of a curve and zoom in, it almost looks like it's linear. So here's what we can do. We can approximate this with a rectangular solid, where this side has length delta R sub j. This side right here, let's just let it be the average of these two sides. So 2 pi R sub j star delta theta sub k. And this side is still delta z sub m. Since this is a rectangular box, we know how to find the area of the volume of that. The volume, delta v sub j k m, is going to be the length times width times height of this. And when we multiply these three together, we get 2 pi r sub j delta theta sub k, which is this, times this side right here, times the length of this side right here. And so then, what do we have? dv, when all these things shrink down towards 0, dv is going to be 2 pi r d theta dr dz, which is basically what we have in this approximation formula for this wedge. So this is what we're going to use when we integrate over some solid region in space using cylindrical coordinates. So let's look at the moment of inertia for our solid cone. We're going to assume that the cone has height h and radius r and has a mass density ρ. Then the mass of this solid cone is just the volume of the cone times the mass density. We're assuming uniform mass density, so V times rho. The volume is 1/3 pi r squared h, and we're multiplying that by rho. So in that case, if we look at one differential mass element moving in that rotating cone, we'll have the following kinetic energy of rotation. The kinetic energy sub kjm is going to be 1/2 the mass of that wedge. We may see it up here in this diagram, this wedge. The mass of that wedge times r squared times omega squared. And the mass is just going to be rho times the volume of that little wedge. And so we get the kinetic energy is 1/2 rho times delta v sub jkm times the radius r sub j squared times omega squared. So to get the total kinetic energy of rotation for that cone, we would add up the kinetic energies of all the little sub-elements, sub-volumes that we have in that cone rotating about the axis of symmetry of that cone. And so that's going to be about 1/2 the sum over the indices j, k, and m, the mass of the jkmth little sub-region, times the radius from the axis of symmetry to that mass, that radius squared, times omega squared. And then for this mass here, that is going to be the mass density times the volume of that little wedge. And so we get this sum approximating the total cone's kinetic energy of rotation. Now, if we look at this, we can, for this volume here, delta v sub jkm, we can substitute r times delta theta times delta z with the appropriate subscripts here, times r sub j squared times omega squared. We look at this and we realize that we have a Riemann sum which in the limit is going to be an integral. In this case, a triple integral. In order to set up our triple integral later as an iterated integral, we need to describe the region in three-dimensional space that is the interior of that solid cone, and we want to describe it in cylindrical coordinates. So here's what we have. Let's suppose that our cone has a top like this, and one of the sides of the cone goes down like this, the other side would come up like this, and think of it as a three-dimensional solid. It has symmetry about the z-axis. So instead of looking at the x-axis and the z-axis, I will pick a horizontal axis and I'll just label it r, and r is in the xy plane, and the origin of this coordinate system is the same as the origin in the xyz coordinate plane, but in two dimensions we'll call it 0, 0. Now, the cone has radius r, this length right here, which is the same as the length from the origin to right here, assuming this is a perpendicular line dropped to the r-axis. So this distance here is also r. This coordinate on the little r axis is capital R. On the other hand, the height of this cone from the vertex of the cone all the way up to this upper face of the cone is h. So on the z-axis, this number right here is h. That means that the coordinates of this point right here on the outside of that cone in two dimensions is capital R, comma, capital H. Well, the line going from 0, 0 to capital R, capital H by the point slope formula or whatever other formula for equations of line you want to use, the equation of this side in this coordinate system is just z equals capital H over capital R times little r. So in that case, we can say that the cone, now thinking about three dimensions again, and what we have here is kind of just a slice of that three-dimensional situation. The cone is going to be the set of points with polar coordinates r, theta, and z, where theta goes from 0 to 2 pi, little r goes from 0 to r, capital R, and z goes from any point here, which is capital H divided by capital R times little r, all the way up to h. So z is going to be in the interval from capital H over capital R times r to h. And so here we have our description of our cone in polar coordinates, and we will use this later to set up our triple integral over that cone in terms of an iterated integral. So let's remember that the cone, written the interior of the cone, that three-dimensional interior, can be written in terms of polar coordinates. It's a set of points r, theta, z, where theta is between 0 and 2 pi, little r is between 0 and capital R, and z is between capital H over capital R times little r and capital H. In this description, capital R is the radius of that cone, and capital H, which appears here and here, was the height of that cone. We saw on a previous slide that the total rotational kinetic energy of the cone was approximated by this sum. We got that by partitioning the cone into little pieces. Each piece we represented using cylindrical coordinates, and then we summed the energies of all of those pieces rotating about the axis of symmetry of that cone. Little r was the distance of one of the little masses from the axis of symmetry, and it was indexed by j. For different j's, we had different pieces of the cone, and so different radiuses. So just rewriting this, we can move this r squared omega squared over to here, and we still have all of these factors also. And then this triple sum is a Riemann sum approximating a triple integral. And we can write that triple integral as an iterated integral, which is shown right here. We have 1/2, which came from here obviously. Theta goes from 0 to 2 pi, little r goes from 0 to capital R, and z goes from h over capital R times r to h. These limits on these iterated integrals just came from the description of the cone up here. And so then it's multiplied, it's integrated over this stuff. But here we have basically r times delta theta times delta z. And so when you take the limit as all of the small volume submasses have dimensions going to 0 and the number of submasses going to infinity, we can replace this in this Riemann sum with the corresponding r dr d theta dz coming from our theory of integration. So the total kinetic energy of rotation of that cone is given by this. But when we look at this, we notice that omega doesn't depend on any of the variables we're integrating over, theta, r, and z. So this, as far as the integral is concerned, is a constant factor inside the integrand, and we can pull it outside right here. So here's the total kinetic energy of rotation for that cone as we just saw before. And now remember, we had an r squared times r dr d theta dz. The r squared times the r was combined to just give us an r cubed term here. Now, if you look at this, the first thing we're doing is integrating on the inside with respect to z, starting from here, going to here. So what do we have? As far as this inside integral goes, there is no z in this integrand, is there? So this is just a constant. So an antiderivative of rho times r cubed with respect to z is just rho r cubed z. And then, by the fundamental theorem of calculus, we would substitute z equals h and z equals h over capital R times r into that and subtract. And when we do that, we just get the remaining double iterated integral here of rho times r cubed as we had here, and this inside integral with respect to z is this stuff times h minus capital H over capital R times r. So now this stuff is integrated with respect to r and theta. So the next thing we need to do is integrate this stuff right here with respect to r going from 0 to capital R. Well, if you look at this, we have an r cubed here and times this stuff right here. So it's going to be r cubed times h minus, and then r cubed times this stuff is going to give us h over r to the fourth. So going from this integral up here down to this integral right here, we didn't do any anti-differentiation yet. We just did a little bit of algebra. R cubed times this factor by the distributive law is this stuff right here. We will continue this in the next transparency. So this is what we saw so far, and after doing a little bit of algebra. And now we're integrating this stuff with respect to r, little r going from 0 to capital R. Well, let's see. This stuff is basically treated as a constant, and so we're integrating this stuff with respect to r. Anti-differentiating an antiderivative of hr cubed is h times 1/4 r to the fourth, minus an antiderivative of this constant times r to the fourth is that constant times r to the fifth over 5. And what we're doing is we're substituting in little r equals 0 and capital R. We're using the fundamental theorem of calculus here, the relationship between integrals and antiderivatives, to get this step. When we plug little r equals capital R into this thing, then substitute little r equals 0 into this thing, and subtract those two things, after just a little bit of algebra, what you will find out is this stuff evaluated at these two limits and subtracted just gives us h times capital R to the fourth minus h over capital R to the fifth over 5. You can see that pretty easily up here, because if you plug in little r equals 0 into this, both of these terms are 0, 0, 0 minus 0. And when you plug in little r equals capital R, that's just going to give us a capital R to the fourth here, a capital R to the fifth here, which is exactly what we have down here. And we also have these factors. And after we do that, we're down to just one integral. The integral from theta equals 0 to 2 pi of this stuff times rho omega square d theta. We have an integral here with respect to theta, d theta. Well, let me just say that again. We have 1/2, and then we have this integral, theta equals 0 to 2 pi of this stuff times rho times omega square times d theta. This is just a single one variable type integral, the type that you would see in Calculus 1. So this is what we just saw a minute ago. And so let's see, we're integrating theta equals 0 to 2 pi, all of this stuff d theta. Notice that none of this stuff here is a function of theta. So if you integrate a constant d theta, theta going from 0 to 2 pi, that's just equal to 2 pi times that constant that we had in the integrand. And we had a factor of 1/2 outside the integral. We have not forgotten it, it's right here. So the total cone kinetic energy of rotation is given by this. Now, we're almost done. All that's left to do is a lot of algebraic simplification. So if you look at this and simplify just a little bit, we have 1/2 times 2 pi times rho times omega square, which we have right here. These two things, if you get a common denominator, and also notice that r to the fifth over r is r to the fourth, this stuff right here simplifies to this stuff right here. And so in that case, we have our answer for the total kinetic energy of rotation for that cone. We can still do some algebraic simplification. We have 1/2 times 2 pi here, which turns out to be a pi. We have this factor here, which we have right here, and we have rho omega squared, which we have those factors here and here. So we're getting pretty close to the end of this problem, but we have not gone all the way yet. We can simplify this just a little bit more. So here's what we have so far for the total kinetic energy of rotation for that cone. And we're going to simplify it a little bit, and we're going to get an answer, it turns out, in terms of the radius of the cone and the mass of the cone. And I is the moment of inertia. So let's see, we have this for the total kinetic energy. But let's remember that the mass density was equal to the mass of the cone divided by the volume of the cone. The mass of the cone, just leave it as m. The volume of the cone is 1/3 pi r squared h. We can simplify this fraction to 3m over pi r squared h. So let's see what that does for us. The total kinetic energy of rotation then, as we saw up here, is just written in a slightly different way. Pi over 20 rho times h times r to the fourth omega squared. And so let's see where we went from here. The pi over 20 is right here. The rho is what? Rho is 3m over this stuff right here. So for this rho, we'll plug in 3m over that stuff. And then we have h r to the fourth omega squared, which we just copied as factors here, h r to the fourth omega squared. Now, if you look at this, we have a factor of h in this expression right here. In this fraction, we have a factor of h in this denominator. There's some cancellation that can go on. We also have an r to the fourth here, and in this factor here, we have an r squared in the denominator. So when you do the simplification, noting those two facts, this stuff can be simplified to 3/20 r squared m omega squared. But let's remember how we define the moment of inertia of any object, in this case a cone. The total kinetic energy of rotation is 1/2 I omega squared. And we just found out that that total kinetic energy is equal to this stuff right here, 3/20 pi r squared m omega squared. So that tells us that 1/2 I omega squared has to equal 3/20 pi r squared m omega squared. Setting these two things, as we did right here, equal, we can solve this algebraically for I pretty easily. Divide both sides of this equation by omega squared. That gets rid of this factor, gets rid of this factor. Then multiply both sides of this equation by 2. And after we do that, we have that I, the moment of inertia of this cone, is just 3/10 r squared times m. So this is an interesting result. We got that the moment of inertia for a cone only depends on its geometric properties, the radius and the total mass. Interestingly, we don't have the mass density in this because we figured out that there was a relationship between the mass density and the mass, which allowed us to get rid of that mass density in this equation up here, resulting eventually in what we have down here. So what did we do? First, we defined the moment of inertia I for a solid. The kinetic energy of rotation about an axis is 1/2 I omega squared. The moment of inertia I depends on the geometry of the solid you're looking at and what axis you are rotating about. Second, we define the cylindrical coordinate system r, theta, and z. We found that for this cylindrical coordinate system, dv is equal to r dr dz d theta, and you can put these factors right here in any other order that you want, whichever will help you solve the problem the easiest way. Then we approximated the kinetic energy of a cone rotating with an angular velocity omega. We approximated it by a Riemann sum. Then, in the limit of these Riemann sums, as the number of small sub-volumes goes to infinity and the dimensions of each sub-volume go to 0, this turned into a triple integral. We evaluated this triple integral by using an iterated integral in cylindrical coordinates. After evaluating that triple integral by evaluating the iterated integral, we found out that for a cone, the moment of inertia is equal to 3/10 r squared times m. You could look up this formula for the moment of inertia of a cone or other geometric solids easily using the internet these days. But the point isn't to get this particular formula unless you happen to be working with cones for some reason, but the technique for finding the moment of inertia is the important part here. What is the moment of inertia? How do we calculate kinetic energies in this case? And how do we use the relationship between those two when things are rotating to find the moment of inertia? I would like to thank you for watching this video. Please stay tuned for more videos coming up.